This video is about rates of change, primarily average rate of change. This is AP Precalculus topic 1.2. If you appreciate this content, please give it a like. The average rate of change between any 2 points on the graph of f of x is the slope through those points. Therefore, the average rate of change formula between 2 points can be simply given by the slope formula, y minus y over x minus x. However, I would prefer that you think of it this way. The average rate of change of f of x on the closed interval from a to b is f at b minus f at a divided by b minus a. And yes, this is another way of saying y2 minus y1 over x2 minus x1, but this is how we do it in AP Precalculus and AP Calculus. To find the average rate of change on the interval from a to b, the first step is to find the y values of those endpoints, and then you can go ahead and find the slope between the endpoints. Let's briefly calculate the average rate of change of this function on the closed interval from -4 to 0. So we do y2 minus y1. So that's 4 minus 0. And then divided by x2 minus x1. So that's 0 minus -4. 4 minus 0 is 4. 0 minus -4 is 0 plus 4, which is 4. So of course we get 1. Again, that is just the slope that we can see. The rise over run is giving us a slope of 1. So we didn't really have to do all of these calculations, but I wanted to show you the connection between the slope and the average rate of change formula. Example 1. Find the average rate of change of the following functions on the given intervals. Part A, f of x is equal to negative x to the third power plus 3x on the closed interval from -2 to -1. First, we need the y values at these endpoints, starting with f at -1. So substituting -1 for x, we have this. -1 cubed is still -1, so we are left with the opposite of -1, which is +1, plus 3 times -1, which is plus -3. That is -2. Next, we need the value of the function at the other endpoint, f at -2. So substituting -2 in for x, we have this. -2 cubed is -8. Opposite of -8 is +8. So we have +8 plus -6. That's +2. Now we are ready to calculate the average rate of change. F at b minus f at a will be f at -1 minus f at -2. And then over b minus a. So that's divided by -1 minus -2. But we already found that f at -1 was -2. So we have -2 minus, and then f at -2 was +2. 1 minus -2 is this. -1 minus -2 is the same as -1 plus 2. So this will give us -4 over +1, which of course is equal to -4. So this is the average rate of change of f on the closed interval from -2 to -1. To find the average rate of change of h of x on the closed interval from 1 to 4, we begin by finding h at 4. So that will be 4 plus 1 over 4 plus 6. So h at 4 is 5 over 10. So h at 4 is 1/2. Next, we need to find h at 1. H at 1, let me put a vertical line here. So h at 1 will be 1 plus 1 over 1 plus 6. So h at 1 will be 2 over 7. The average rate of change will be h at 4 minus h at 1 divided by 4 minus 1. So that is 1/2 minus 2/7 divided by 4 minus 1. We need like denominators, so let's multiply 2/7 by 2 over 2, and let's multiply 1/2 by 7 over 7. So this will give us 7/14 minus 4/14 divided by 3. 7/14 minus 4/14 is 3/14. So we have 3/14 divided by 3. When you divide a fraction by another number, you just multiply the thing you're dividing by into the denominator. For example, a over b divided by c will just be a over b times c. So 3 over 14 divided by 3 will be 3 over 14 times 3. And then these 3's will simply cancel each other out, and you get 1 over 14. So this is the average rate of change. Example 2. The graph of g of x is shown below. Find the average rate of change of g of x over the closed interval from -1 to 3. So the endpoints are here at -1, 0, and here at 3, 4. We could use the average rate of change formula, or we could simply recognize that the average rate of change is just the slope between these endpoints. So it's just going to be rise over run. So this is up 1, 2, 3, 4, and over 1, 2, 3, 4. So it's going to be 1. On a problem like this, when you're given a graph, it's a little bit silly to go through the motions of finding f at b minus f at a and then dividing by b minus a. Just do the slope like you did in Algebra 1. On the other hand, if they say show the calculations that lead to your answer, then you have to go through those motions. Instead of f, we have g. So f at b minus f at a becomes g at 3 minus g at -1 divided by 3 minus -1. G at 3 is 4, and g at -1 is 0. So that's 4 minus 0. 3 minus -1 is 3 plus 1. So that is 4 over 4, which equals 1. Example 3. The table above lists the life expectancy of U.S. females born in a given year. Find the average rate of change in the life expectancy of U.S. females born from 1850 to 2000. Include units of measure. We are using the function a of t for life expectancy. So f at b minus f at a over b minus a becomes a at 2000 minus a at 1850 divided by 2000 minus 1850. A at 2000 is 81.83 years, and a at 1850 is 46.10 years. This is looking like a calculator active problem, so I'm going to use the calculator from here. Make sure you know how to make a proper fraction on your calculator. This software is a little bit old, so I have to hit alpha y equals enter. Your calculator will do that too, but there's probably a shortcut. If you hit alpha and then x, it will probably make a fraction right away. Kabam! The average rate of change is 0.2382. Let's add units. In the numerator, we were subtracting age years. In the denominator, we were subtracting birth years. Let's just say the average rate of change of the life expectancy is 0.2382 age years per year. We've been finding the average rate of change of a function over an interval, but can we find the instantaneous rate of change? The idea of instantaneous rate of change is equivalent to finding the rate of change of a function at a given point. The concept is developed formally and used in calculus, but we can approximate the rate of change at a point by using the average rate of change over small intervals. Example 4. A ball is thrown vertically in the air. For times between 0 and 5, the height of the ball is modeled by the function h of t equals negative 4.9 t squared plus 25t plus 5, where h is measured in meters and t is measured in seconds. Find the average rate of change in the height of the ball over the following intervals. Include units of measure. Looking at all of these decimals, I'm assuming this problem is calculator active. So let's go ahead and type in h of t as y1 in the graphing calculator. As usual, we will have to use x's instead of t's. Hit the y equals button and type in h of t like this. For part A, the average rate of change of h on this interval will be given by this expression. Let's type this into the calculator. Quit your way out of this, hit second quit, set up a proper fraction however you do it. I have to hit alpha y equals enter, but again you can probably hit alpha x and make a nice fraction. So I want h at 1.1 minus h at 1. We have h typed into y1 on the calculator. So I'm going to type in y1 at 1.1 minus y1 at 1. So how do I make that show up? If you hit alpha trace enter, that makes y1 show up. And then you can just use parentheses just like you would write on paper. So y1 at 1.1 is really h at 1.1 minus y1, so alpha trace enter at 1. And then, so this is like f at b minus f at a over b minus a. So divided by 1.1 minus 1. So this is the average rate of change for part A, 14.71. Don't forget the units. Since the height h is measured in meters and the time is measured in seconds, we have 14.71 meters per second. For part B, the average rate of change on this interval will be given by this expression. Let's type it in. I'm going to walk you through it one more time. Set up a proper fraction, and we need y1 at 1.01. So that'll be alpha trace enter at 1.01 minus y1 at 1. So alpha trace enter at 1 divided by 1.01 minus 1. So the average rate of change on this interval is 15.151. Notice that in part A, we found the average rate of change of h on a small interval, and then in part B, we found the average rate of change on an even smaller interval. For part C, we will make that interval smaller still. Here's the expression for the average rate of change of h on this tiny interval. Let's type it in. 15.1951. This is the average rate of change on a tiny interval very close to t equals 1. For part D, we will find the average rate of change on an equally small interval, but from the left side of t equals 1. Here's an expression for the average rate of change of h on the tiny interval just to the left of t equals 1. Type it into your calculator like this, and let's take a look. 15.2049. Based on example 4, what do you think is the true rate of change in height of the ball at time t equals 1 second? Since the rate of change on a small interval to the right of t equals 1 was a little bit below 15.2, and the rate of change on a small interval to the left of t equals 1 was a little bit above 15.2, then the rate of change of h of t at t equals 1 second is probably 15.2 meters per second. The rate of change of a function at a particular point is the rate that the y values would change if the x values changed at that point. This concept is what we will call instantaneous rate of change later in calculus. While we cannot find the rate of change at a particular point in AP Precalculus, we can do the following two things. We can either estimate the rate of change at a point by finding the average rate of change over a very small interval, like we just did, or we can estimate the rate of change at a point by estimating the slope of a tangent line. Note that when we discuss the rate of change of a function, we are essentially discussing the slope of the graph. Notice that an increasing function like this one will have a positive rate of change at every point. That's because for an increasing function, no matter where you put the tangent line, it always has a positive slope. Again, if f of x is increasing, the rate of change is positive because the slope is positive. Similarly, for a decreasing function like this one, the rate of change will be negative, because the slope of the tangent line at any point will be negative. I've given you this information before in chart form, but hopefully you have a better understanding of why this part of the chart is true. Example 5. For each scenario below, determine whether the two quantities typically have a positive rate of change or a negative rate of change. Two quantities will have a positive rate of change if the quantities increase together or decrease together. Two quantities will have a negative rate of change if, as one quantity increases, the other one decreases. Part A. What about a child's age versus the child's height? These quantities will have a positive rate of change because as the child's age increases, the child's height also increases. Part B. What about a golfer's skill level versus the golfer's score? These two quantities will have a negative rate of change. To understand this answer, you need to understand that the point of golf is to get the ball in the hole using the lowest number of strokes. The golf score indicates how many strokes it took you to get the ball in the hole. So, as a golfer's skill increases, the golfer's score will decrease. Part C. What about the height from the ground of a coin dropped off the Burj Khalifa versus the speed of the coin as it falls? I have no idea how to pronounce that, by the way. But I know that the height of the coin from the ground and the speed of the coin as it falls will have a negative rate of change, because as the height from the ground decreases, the speed increases. The graph of f is shown along with the line tangent to f when x is equal to -4. In calculus, we will learn that the slope of the line tangent to the graph of f at any given point is the true rate of change of f at that point. In other words, in calculus, we say that the instantaneous rate of change at a point is the slope of the curve at the point. In AP Precalculus, we cannot precisely calculate the instantaneous rate of change because we cannot calculate the slope of a curve at a point. However, we can estimate the instantaneous rate of change by sketching a tangent line and estimating the slope of the tangent line. Example 6. Estimate the rate of change of f at x equals -4 using the slope of the line tangent to f at x equals -4. Right here, the tangent line comes very close to the point -2, 5. And then on this end, the tangent line comes very close to the point -6, -0.5. So let's estimate the slope of the tangent line by using these 2 points. Using the slope formula from Algebra 1, the approximate slope of the tangent line will be 5 minus -0.5 over -2 minus -6. Minus a negative is addition, so we have 5 plus 0.5 over -2 plus 6. This is 5.5 over 4. Which is 1.375. Remember, this is an approximation, so someone else may come up with an answer that's a little different but equally valid. Example 7. Sketch the tangent lines to f at the 5 points indicated on the graph above. Here are the 5 tangent lines, all shown in different colors. Example 8. Does the graph of f appear to have a greater rate of change at x equals 4 or x equals 5? Explain your reasoning. The blue line is the tangent at x equals 4, and the orange line is the tangent at x equals 5. F of x appears to have a greater rate of change at x equals 5 because the slope of the tangent at x equals 5 is greater than the slope of the tangent at x equals 4. The orange line is a little bit steeper than the blue line. And here I have simply written down what I just said. I need you to memorize the relationship between the rate of change of f and the graph of f. The rate of change of f will be positive wherever the graph of f is increasing, and the rate of change of f will be negative wherever the graph of f is decreasing. Also, the rate of change of f is increasing wherever f is concave up, and the rate of change of f is decreasing wherever the graph of f is concave down. If this information sounds familiar, it's because all this information is on this chart that I've already asked you to memorize. Let's see if you can do example 9 without looking directly at that chart. The graph of f is shown above. Complete the blanks below to correctly describe the graph of f and the rate of change of f. The graph of f is increasing or decreasing. It is clearly increasing. It is rising from left to right. And concave up or down. This is concave down. It is part of a frown. Because the rate of change of f is what and what? Well, we have learned that if f is increasing, then the rate of change is positive. And we have learned that if f is concave down, then the rate of change is decreasing. But here it is on the chart just in case you need it. If f is increasing, then the rate of change is positive. If f is concave down, then the rate of change is decreasing. Eventually, I need you to know the information on this chart so well that you don't have to write it down. Until then, I want you to practice writing this chart from memory. At the beginning of your next test or quiz, you should write this chart on a piece of scratch paper or in the margin. Example 10. For each of the following graphs, circle the correct descriptions for the behavior of each graph. Here's the graph of f. The graph of f is positive or negative. Well, f is above the x-axis, so it is positive. Also, the graph of f is increasing or decreasing. You can see that it is falling from left to right, so the graph of f is decreasing. How about the rate of change of f? Is it positive or negative? Well, if the original graph is decreasing, that means that the rate of change is negative. Is the rate of change increasing or decreasing? If f is concave up, that means the rate of change is increasing. We answered those questions without looking at the chart, but if you need it, this chart will save you. When f of x is decreasing, the rate of change is negative. When f of x is concave up, the rate of change is increasing. Let's try to do the next one without looking at the chart. The graph of g is positive or negative. It is below the x-axis, therefore it is negative. The graph of g is increasing or decreasing. It is clearly rising from left to right, so it is increasing. Now, what about the rate of change? Is the rate of change positive or negative? If the graph is increasing, that means the rate of change is positive. Is the rate of change increasing or decreasing? Well, that comes from the concavity. G is concave down. Therefore, the rate of change is decreasing. One more time for the graph of h. The graph of h is positive or negative. It is above the x-axis, therefore the graph of h is positive. Is the graph of h increasing or decreasing? It is falling from left to right, so the graph of h is decreasing. How about the rate of change of h? Is it positive or negative? Well, if the original graph is decreasing, then the rate of change is negative. Is the rate of change increasing or decreasing? We can tell whether the rate of change is increasing or decreasing based on the concavity. H is concave down, therefore the rate of change is decreasing. One more thing. Another way to determine whether the rate of change is positive or negative is to remember that rate of change means the slope on a graph. For the graph of f, the slope of a tangent line is negative, therefore the rate of change is negative. For the graph of g, the slope is positive, so the rate of change is positive. And on the graph of h, the slope of the tangent line is negative, so the rate of change is negative. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.